So coming up later in the slideshow, slide 8, it looks like it is just a 2-minute video of something that I found really, really cool. It's one of the coolest labs I was able to do during first year university physics. I admit at that time I did not understand too well what was going on because in high school I actually never learned any electromagnetism. My teachers got up to momentum, so we did the conservation of momentum and elastic collisions. But we never made it much further than that. You guys have made it further than that, so we're getting into the electromagnetism. And yeah, there's a few examples we're going to do here leading up to that video I was talking about, which I hope you can find pretty cool as well. That we can actually see these effects that we're talking about, of these charges feeling a force by magnetic fields, even though magnetic fields are invisible and charges are really, really small. How can we possibly see them? There was actually a nice setup that I got to use in first year, and I found a video on it from people at Rice University, I believe, doing that. So the few examples here will lead up to that, starting with this one. Suppose there is a uniform magnetic field into the page as shown. So that would be represented by all those circles with X's on them. That's the B field, that's into the page. So that's where your middle finger is going to point as you do the right-hand rule number 3 for all of these charges. Well, we won't do all of them, hopefully we'll see a pattern after we do a few of them. For the 8 protons shown, and it's important you know they're protons, so they're a positive charge. That means that our index finger needs to point in the direction of the velocity. If they were negative charges, if they were electrons, we'd actually have to point our index fingers in the opposite direction. The arrows drawn represent their velocities at this specific instant, determine the direction of the magnetic force on each of them at this instant. So I'm going to start with the particle at the very top, the proton at the very top. It's got a velocity going directly to the left, so that's where my index finger needs to point. And it's got, everything here is in a magnetic field into the page, and that's where my middle finger has to point. So I'll put my pencil down because I'm right-handed. I put my 3 fingers at all 90-degree angles to each other. It's got to involve some dexterity with your wrist. So my index finger is pointing left, my middle finger is pointing down. So which way does my thumb stick out? My middle finger is pointing into the page. So which way is my thumb sticking out now? It is pointing down. So this top particle here feels a force that is directly down. I'm going to move over to the next particle. I'll go counterclockwise here. So I have 2 options. I can move my whole arm and twist my wrist and shoulder joints a little bit. Or I can actually leave my arm and hand in exactly the same position it is in now and rotate my iPad. If you have a piece of paper, that might be what you do, but you guys are on your Chromebooks probably, so that actually might be pretty difficult. So you might have to rotate your wrist and arm. But same thing, I have my index finger that I need to point in this angle. I got my middle finger that I need to point into the page, and I ask which way does my thumb stick out after that, and it will stick out at this 90-degree angle to the velocity and also 90 degrees to the magnetic field. So I'm not going to do all 8. Hopefully you can recognize what's going on here after a few. So I'll do one more, the next one over. I'll rotate my iPad again a little bit, rotate my wrist and shoulder a little bit again, but I need my index finger pointing down this time. My middle finger stays pointing into the page, and I ask which way is my thumb pointing now. That would be to the right. Okay, so I'm pretty confident that there's a pattern going on here. So instead of, I'm not actually going to do the right-hand rule for the rest of these particles. I'm going to just draw what I think the pattern is. I think they all point towards the center of, what shape are we talking about here? Well, technically, since I just have 8 charges here, if I were to draw a line connecting all 8 charges, it would make an octagon. However, what if I asked for 10 charges? It would be a decagon. 20 charges, I don't know, I call that a 20gon, I guess. There might be a name for it. But what about an infinite number of charges? Then we're actually talking about a circle. So this is one major concept here, is that if I have protons placed all along this circle and all moving in the circular direction, the force, the direction of the force on any of these protons is always going to be pointed where? Well, it looks like it's always going to be pointed towards the center of that circle. So you may recognize that situation from Unit 1, the very last part of Unit 1. It's called uniform circular motion, when the net force on any object moving in uniform circular motion is always pointing towards the center of the circle. And we call that a centripetal force. And that turns out to be exactly what happens to these charged particles that are fired into a uniform magnetic field. It's important that it's uniform. It's the same strength throughout this whole page. And if the charge is fired perpendicularly to it at a 90-degree angle, then it'll travel in a perfect circle.